All right, lecture 20, again in chapter 8. And the goal of lecture 20 is to show you ideas on, or show how one increases the efficiency, the power efficiency of vapor power cycles. So we start by improving basic Rankine cycles by adding something called reheat. And then we'll get to the concept of regeneration. And we'll see only one of the two ways in this lecture. The second way will be in the next lecture, and that way is called open feed water heaters. So what is a reheat cycle? Well, in a reheat cycle, you start from the steam generator here, and you divide your turbine into two stages, a high pressure stage, a first stage of the turbine, and a low pressure stage, second stage of the turbine. So you send the water, the steam in this case, through the high pressure stage, and then you take it back and you send it a second time in the steam generator in something that's now called the reheat section of the steam generator here. So then you send that full flow of steam into the second stage of the turbine. It will be at a lower pressure because you have lost pressure between 1 and 2 in the first stage of the pressure of the turbine. It will be at a lower pressure. The pressure here will be the same as the pressure there because this is a heat exchanger, that's just a tube. But it will be at a higher temperature because it has been reheated. Then the lower stage turbine expands it again until you get to point number 4, at which point it goes from the condenser, the pump, and the rest is all the same as the classic Rankine cycle. So if we look at the TS diagram, we start at the same point 1 where we started before. We go through the first stage of the turbine, and if that works isentropically, we go from 1 to 2. And then we go back into the reheat section of the steam generator from 2 to 3, at which point we go into the second stage of the turbine that sends it from 3 all the way to 4, and then the rest of the cycle is the same. We then condense the water in the condenser to 5, pump it back up to 6, and then get back through the steam generator to point number 1. Now, the flow, of course, of water is the same throughout the whole cycle, and the total work of the turbine is the work of the first stage plus the work of the second stage. So it's going to be H1 minus H2 plus H3 minus H4. But H3 is, of course, different from H2 because you reheated your steam. So why does one do that? Well, the first thing, the most important reason to do this is that having a turbine work over a two-phased flow means that the turbine will have an increased amount of liquid water droplets impacting its blades here. And so these droplets of water that impact the blades erode the blades and create wear on the turbine. You really want your turbines to work as much as possible on high quality steam. And in fact, that is the reason why this X fraction is called quality. It's because the higher the quality of the steam, the less damage it does on your machines. So this is a quality of 1, and you want the quality to be as high as possible to decrease this problem. The second thing you do is the increased boiler pressure, because you can work at this higher pressure for a longer time, that increases the amount of work you do. In fact, this is point number 3, but it's also point number 6. If you remember that the work that the system does is the area under the curve in the TS diagram, you have actually simply added, if you compare the cycle that goes from 1 to 2 to 4, to a cycle that goes from 1 to 2 to 3 to 4, you have added this much more work to your cycle, whereas you haven't actually increased the maximum operating temperature of the pipes. So this is all beneficial. Thirdly, you have increased the average amount of time that the steam spends at a higher temperature. Higher temperature means higher Carnot efficiency. So this cycle with reheat is more efficient also as a conventional cycle with just a supersaturated steam without reheat. More work, more efficiency, less wear on the parts. This is a win from every perspective. If you want to drive the same advantages to an even higher point, then you actually never, in your steam generator, cut through the vapor dome. You have your steam generator take high pressure water and then send it all the way to this above the critical point into a supercritical cycle, which is here at 1. And then you can get a point number 2, a reheat to 3, and a point number 4. And you have now noticed that point number 4 is even closer to a quality of 1. So you really have the same benefits as you had with the cycle with the conventional reheat, but you just drove those benefits much higher yet. There is, of course, a little disadvantage, and that is that supercritical steam is actually quite dangerous. It's high pressures, it's very high temperatures, so it puts constraints on the metallurgy of all the tubing and the machines, but it's clearly an advantage. Now, something that actually helps with the quality, but not with the efficiency, of course, is that the cycle is not ideal. So these turbines, first stage is not an isentropic from 1 to 2s. It is a machine that has a finite isentropic efficiency, so it gets you to a point that has a higher entropy. Point 2 has a higher entropy than point 2s. So we have gone through calculations of entropic efficiency, isentropic efficiency of the turbines. That applies here. And of course, it costs in efficiency. It does win. One benefit is that the quality of the steam is higher at point 2s than it was at point 2 than it was at point 2s. The same thing happens in the lower stage, the low pressure stage of the turbine. So going from 3 to 4s, which would be isentropic, you actually go to a point that has a little bit more entropy, and it has a little bit more quality, but of course you have a loss in efficiency. The next technique that we use to increase the efficiency of a Rankine cycle is the concept of regeneration. Now that is a little bit more complicated. So let's start from a conventional Rankine cycle. 1, 2, 3, 4a, or even 1 with a that works in superheated steam, 1 prime 2 prime 3 4a. One of the reasons that you have relatively low efficiency in such a conventional Rankine cycle is the fact that this point A is the point where you have to heat your liquid water, and that temperature is relatively low. So we saw before that we can actually simply go supercritical and avoid this problem, go to a temperature for point A that is much higher. That's above here. But even if you don't want to do that, or even if you do want to do that, this critical point is relatively low. And so that limits the Carnot efficiency. So an alternative form of heating is to use heat that comes from this fraction of the liquid water to preheat the liquid that you're going to feed into the pump, or after the pump, the liquid that you're going to feed in the steam generator. If you do that, you use heat that comes internally from the cycle itself, not heat that comes from the boiler or the steam generator. But on the other hand, you have to have heat that comes at a sufficiently high temperature. So you have to have heat that comes from here somewhere, temperature that comes from here somewhere, and use that to preheat the water here. Okay, so that is how the concept works of regeneration. Extract heat from this portion of the cycle to increase the heat at this portion of the cycle. And since this heat comes entirely from internal sources, from the cycle itself, that heat doesn't count toward your Q-in term, which is the heat that solely comes from your steam generator. So that should, in principle, improve the efficiency by having the cycle spend more time at the high temperature end. Okay, so how do we do that? And that looks nice in theory. But what you do is you increase the temperature of the fluid before it is sent into the steam generator, before it is heated, making the cycle spend more time at a high temperature. And so basically, you have a transfer of heat in the steam generator that is more isothermal, if you want, because you have less of a temperature difference to take care of in the boiler itself. So it's a little bit more like a Carnot cycle because you transfer heat at a higher temperature. Okay, so the way we do this is by taking some water from the high temperature part of the cycle and mix that with water at the low temperature part of the cycle. This mixing, it's actually not the water, doesn't have to be mixed. What has to be done is the heat has to be transferred from water at the high temperature part of the cycle to the low part of the cycle. So you can do it indeed by mixing, which is then called a technique called open feed water heaters, direct contact type heat exchanger. And you can do it with closed heat exchangers, shell and tube heat exchangers, like we explained. That's then going to be called closed feed water heaters. This is a technique that's general. For example, it's used also in distillation. Okay, so let's take a look at a cycle with an open feed water heater. We come out of the steam generator with a mass flow rate m dot here at point number 1. We send that mass flow rate through a high pressure stage of the turbine. So we expand that water to a certain extent, but we don't send it through the whole turbine. In the middle of the turbine, we bleed off a fraction of this water. So at point number 2, we bleed off fraction y of this water. So the mass flow rate here is m dot. The mass flow rate at point number 2 is then m dot times y. The rest of the water is sent straight through the low pressure turbine into 3. But the flow that's here then is m dot times 1 minus y, because m dot y goes here. This is treated like usual, goes through the condenser and goes through the first pump, and comes here in essentially what is a mixing chamber. It's called an open feed water heater, where y and 1 minus y flows join each other, so that now you have the full y flow, the full 1 unity m dot flow, goes out in point number 6, goes to a second pump, and is sent to the steam generator. Obviously, these pumps have to be balanced for their pressures. So because this is one open vessel, the pressure that comes in here and the pressure that comes in here has to match. So this pump has to match its pressure so as to match the pressure at the point of the turbine where you have bled off the water. And of course, the pressure in point number 6 is the same as the pressure in point number 5 or pressure at point number 2, because otherwise there would be backflow toward the region of lower pressure. So you have to have everything be isobaric between 2, 6, and 5. That balancing work is by adjusting the pumps. Well, so this is a repeat of what I showed you. Now here is the TS diagram, and I will spend the next few graphs in explaining how we get into the details of this TS diagram. So I just repeat what we had before. The mass flow rate is unity here, goes into 2 fractions in the turbine, bleed water and straight water. Let's do it. So here are my states. State number 1 is here. It's a high pressure, high temperature side of the cycle. We go through the first turbine. So the full flow, 1, goes through the first turbine between 1 and 2. That's okay. 1 is just the fraction, the unity fraction of the mass flow rate. Now we separate that into a fraction y that is bled off the turbine here. So fraction y is at state number 2, notice that, and fraction y flows between 2 and state number 6, which will be here. So fraction y goes across the vapor dome at this level here. Meanwhile, fraction 1 minus y continues through the low pressure stage of the turbine, eventually goes through 3 to 4, goes through the condenser, goes through the pump 4 to 5, and rejoins the open feed water heater, which is here. So this fraction 1 minus y starts here, and it rejoins fraction 6 up here, where it joins fraction y. y and 1 minus y come together at point number 6. From point number 6 on, it gets pumped through this pump to point number 7. It gets sent through the steam generator, and it gets, back to point number 1. So that's how we get to this TS diagram from this schematic. Let's look at the equations. So we have to write, first of all, a mass balance equation. The fraction 1 of m dot goes into a fraction y and a fraction 1 minus y. So y is the mass flow rate at point number 2 divided by the mass flow rate at point number 1 or point number 7, which is the total mass flow rate. Mass balance, though, is that once you go through your open feed water heater, the fraction that comes in, the mass that comes in from y and the mass that comes in from 2 makes up the mass that comes in from 6. And of course, the mass that's in 6 is the mass in 7 is the mass in 1. The second thing we have to write is the energy balance equation, in particular in this open feed water heater. So the mass in 2 plus the mass in 5 divided by the mass in 1. Well, there's the mass in 2 plus the mass in 5 times the enthalpy in 6, that's what you have here, has to be the mass in 2 times the enthalpy in 2 plus the mass in 5 times the enthalpy in 5. So this 2 plus 5 times H6, M2 plus H1 times H5. Divide both by m dot 1. And of course, m2 plus m5 divided by m dot 1 is 1. I pushed the wrong button. So that's that. And this ratio is 1. H6 is H6. M dot 2 over M dot 1, okay, that is Y. So this becomes Y. M dot 5, well, M dot 5 is M dot 6 minus M dot 2, or M dot 1 minus M dot 2, so it's 1 minus 1 times H5. This equation just writes the energy balance equation in the open feed water heater. H2 times Y plus H5 times 1 minus Y is H6 times the unity of the mass flow rate. This equation can be solved for Y also. Y is H6 minus H5 over H2 minus H5. That is simply the enthalpy balance in the open feed water heater itself. That is the same Y as you have here. So basically, you can derive your M2 over M1 from the values that you can read in your tables for the states 6, 5, and 2. And now we can write the equations for the balance of heat and work. So heat, Q in, is of course H1 minus H7. The heat out, well, the heat out only concerns the fraction of 1 minus Y, because that's all that goes through the condenser. So it's 1 minus Y, H3 minus H4. The work in the turbine, well, there are 2 stages to the turbine. The first stage gets the whole mass flow rate. So it's H1 minus H2. That's this term. And the second stage gets only a fraction of the mass flow rate, the fraction 1 minus Y. Here, that's H2 minus H3. 1 minus Y, H2 minus H3. Pumps. Well, there are 2 pumps, pump 1 and pump 2. Pump 2 gets the full mass flow rate because this mass flow rate between 6, 7, and 1 is the full mass flow rate of the system. So its work is H7 minus H6. Now this pump has a lower mass flow rate. It has only 1 minus Y as mass flow rate, and the work it takes is H5 minus H4. 1 minus Y mass flow rate, H5 minus H4. These equations, as well as the ones on the previous graph and these 2 equations, will govern your spreadsheet when you're going to calculate the details of the states in the entire cycle with an open feed water heater. And that's it for today. The next class will be the last one on vapor compression systems, and that is where we will see closed feed water heaters and then alternative cycles.